My name is Matthew McClintock, and this is my video report for Lab 3, Magnetic Field of a Bar Magnet in Physics 2212. The purpose of this experiment is to better understand the distance dependence of a magnetic field of a bar magnet by using the magnetometer on a smartphone. These measurements were then compared to those predicted by a GlowScript code for both on and off-axis fields. The experiment also provided an opportunity to practice calculating the magnetic dipole and manipulating the magnetic field equation. Here is a quick preview of the results. Based on the distance dependence equation, the exponent n was calculated to be negative 2.78. The combination of constants and parameters k was 9.28 times 10 to the negative 7th, and the magnetic dipole was 4.646 ampere meter squared. The primary physics principle for this lab is the Biot-Savart law for the field of a magnetic dipole. The second equation is an approximation for the magnetic field on the axis of the dipole when the distance to the observation location is assumed to be much greater than the distance between the poles of the dipoles. Additionally, there is also the relationship between the magnetic field and the distance away from the bar magnet. The last linearization formula plots the natural log of the magnetic field versus the natural log of r. For the entirety of the experiment, the system only included the magnetometer in the smartphone, while the surroundings encompassed the bar magnet and everything else, including the magnetic field of the Earth. Before performing the experiment, determining the location of the magnetometer in the smartphone was very important for accurate results. Additionally, the bar magnet was aligned perpendicular to the Earth's magnetic field to cancel its effect. The smartphone was rotated until the x component of the magnetic field in the magnetometer app was roughly 0. The procedure of the experiment can be split into 3 parts. First, I recorded the distance along the ruler at which the bar magnet produced 20, 70, 120, 170, and 220 mu Tesla in the phone magnetometer. Next, I rotated the smartphone 90 degrees and determined the distance on the same ruler at which the magnetometer reads 100 mu Tesla. Finally, the smartphone was moved the same distance but perpendicular to the magnet as shown in the final image on the left. After determining the distance to the observation location for each of the magnetic field quantities, I plotted the natural logs of the magnetic field and corresponding distance to achieve a linear plot that showed n equals negative 2.78 and k equals 9.29 times 10 to the negative 7th. The expected n is negative 3. For the magnetic dipole calculation, I set the distance dependence equation equal to the magnetic field on-axis equation and solved for mu. During this calculation, I assumed that r raised to the difference between the observed and expected n was approximately 1. The magnetic dipole was roughly 4.646 ampere meter squared. At the bottom of the slide is the process of converting the perpendicular distance to the net magnetic field when the bar magnet is 45 degrees from the axis. Here is the code and output screen from GlowScript. I started by initiating any physical constants. I then defined a function to calculate the magnetic field of a magnetic dipole and initialize 7 observation locations, including 2 parallel to the magnetic dipole, 4 perpendicular, and 1 off-axis. At the point 45 degrees from the axis, the code calculated the net magnetic field to be 3.97 times 10 to the negative 5th ampere over meters, which is 29.98% less than the hand-calculated net magnetic field of 5.67 times 10 to the negative 5th ampere over meter. Here are some of the most important takeaways from the experiment. We saw that the bar magnet has the same magnetic field as a magnetic dipole, and the magnitude of its magnetic field falls off exponentially as the distance to the observation location increases. A potential source of error, though, was possibly performing the experiment near other magnetic fields like the electronic devices in my room. I could have also inaccurately determined the location of the magnetometer because aligning my smartphone perpendicular to magnetic north was very sensitive. I also had to resort to using a ruler and tape measure to measure the distances because 2-meter sticks were not available to me. If the smartphone magnetometer was not oriented to compensate for magnetic north, all the readings would be equally skewed based on the direction of Earth's magnetic field. If 2 identical magnets were stuck together before performing the experiment again, we could find that the direction of the magnetic field does not change because the second magnet essentially extends the already existing magnetic dipole. However, the magnitude of the magnetic field would double if we assume the lengths of the magnets are negligible compared to the distance to the observation location.